Okay, we're back, and we have some space here, but actually we're not actually going to use this space for a little while. So we want to go to the general case, general n, and in order to do that, we're going to need some new notation, a few new concepts, terminology. So that's what we're going to develop here for the next few minutes. And we're going to start off with the idea of submatrix or submatrices of a given matrix like the A that we're starting with, defining our quadratic form. So here we have a matrix A, a 3 by 3 matrix, so we're already going beyond the case n equals 2. We have a 3 by 3 matrix, and we're going to be interested in the quadratic form on R3 that'll be defined by such a 3 by 3 matrix. And the first new kind of concept we're going to need here is the concept of a submatrix of the matrix A. And a submatrix is really just what the name kind of suggests. It's that we retain some of the rows and columns, but we get rid of some of the rows and columns, leaving us with a submatrix. And so here's the first example. And what I'm doing in these examples is I'm keeping all the entries in A visually for us, but I'm saying we're going to delete the ones that are in green. So you can see that this first submatrix that I've drawn out here is one in which I'm deleting the second column. So it's only the white entries that are now in the submatrix that we have remaining. So in this case, the submatrix is 3 rows by 2 columns because we've deleted one of the columns. And so here's another submatrix where I've still deleted the middle column, and now I've deleted the bottom row. So I've deleted 1 row and 1 column, and I've got 2 rows and 2 columns remaining. And so this submatrix has just the 4 white entries. It's 2 by 2. And last here, in terms of our little 3 by 3 example, I've got an example where I'm deleting still the middle column and now the bottom 2 rows. So I've got a submatrix that's 1 by 2, just A11 and A13. So a pretty simple idea. Okay, so that's a submatrix. But we're actually not going to be interested in general submatrices here, although for other things we are. When we talk about, for example, expanding a determinant by cofactors, we have to look at all kinds of submatrices, just like what we had there, to obtain the cofactors to do the expansion. But for what we're going to do today, we don't need all the submatrices. We just need the submatrices of a particular kind. And so notice in this definition that I've identified the notion of a principal submatrix of the matrix A. And so a principal submatrix is one in which we delete some rows and columns, but we delete the same number of rows as columns. So what remains is still a square matrix, but of a smaller dimension. And if it's a principal submatrix, we delete the same rows as columns. And of course, by the same, I mean if I delete the middle column, then I delete the middle row in a 3 by 3 matrix, for example. Or if I delete the first and third columns, I have to delete the first and third rows. So let's just take an example here. In this example, so we look at our definition here, and in this example is a 4 by 4 matrix A, and I have deleted the second row and the second column, leaving me with a 3 by 3 matrix. And you notice that it's the same row and the same column, in the sense it's the second row and the second column. And now our definition here says that we have to be able to do that for deleting any number of rows and columns. So now we're looking at a principal submatrix of the original matrix A, in which I have deleted 2 rows and 2 columns. I've deleted the second row and the second column, just like in the first case, and I've deleted the 4th row and the 4th column, leaving me with just a 2 by 2 submatrix. And notice that the submatrix then in these principal matrices always contains diagonal elements and pairwise off-diagonal, twin off-diagonal elements. And so in the definition here, we have, it says that order K principal submatrix is when we delete n minus k rows and columns. So that here I've got an order K, order 2 submatrix because it retains 2, that is k, rows and columns, and I've deleted n minus 2, which is also 2 in this case, rows and columns. In the first case, I had a principal submatrix of order 3, so k equals 3, and I deleted n minus 3 equals 1 row and column to get that order 3 submatrix. So that's what we mean by a principal submatrix. So the principal submatrices, unlike general submatrices, are always square, and they have diagonal elements from the original matrix, as a kind of an aside, and they always retain the same numbered rows and columns from the original matrix, and they always delete the same numbered rows and columns from the original matrix. So let's go back here to our definition, and now we've got yet another term, the leading order K principal submatrices, and the leading principal submatrices are the ones where the rows and columns we retain are all the ones to the upper left, and the ones that we delete are all the ones to the lower right. So here we have all the leading principal submatrices of a typical 3 by 3 matrix. So the leading submatrices are, of course, the one where we don't delete any of the rows or columns, the whole matrix, the one where we delete just the rightmost column and row, so that we now have a 2 by 2 principal submatrix. It's a leading principal submatrix because it's the leading rows and columns that are retained. The third leading principal submatrix here is the one where we have deleted 2 rows and columns, but they have to be the leftmost and bottommost 2 rows and columns. So the order 1 principal submatrix is just the principal submatrix consisting of A11. It's 1 by 1. So the leading principal submatrices of a 3 by 3, there are 3 of them, where we have a 1 by 1, a 2 by 2, and a 3 by 3. And so now we can look at the same thing for an original 4 by 4 matrix A, and in that case there are going to be 4 leading principal submatrices, and they are going to be the ones where we have the order 4 principal submatrix is going to be just the original matrix. The order 3 will be one where we delete the rightmost row and column, leaving a 3 by 3. The order 2 leading principal submatrix, we delete the 2 rightmost and bottommost rows and columns, leaving us with a 2 by 2, the upper left part of the original matrix. And the last order 1 leading principal submatrix is the one where we've deleted all but one of the columns and rows, leaving us the one column and row, a 1 by 1 submatrix. So we end up with 4 leading principal submatrices. Notice in our definition here, we also have the notion of a minor of the determinant. I'm sorry, I'm not reading it very well. We have the notion of a minor of a submatrix. So a minor of any submatrix is its determinant, but of course determinants aren't defined for any submatrix. So a minor has to be the determinant of a square submatrix. So for any square submatrix, and of course all of the principal submatrices are square, therefore all the leading principal submatrices are also square, and so the minor of all of these matrices, all these principal submatrices is well defined, and it's just the determinant of that submatrix. So let's just go back over here, and we'll see that where I wrote the 4 leading principal submatrices, now I've written out, typed out, I guess you could say, the 4 leading principal minors, that is, the minors of the 4 leading principal submatrices. So they're all determinants in what we have over here. So those are the new ideas we're going to need. And let's see how those will be used to give us a more general form of the theorems that we had for the n equals 2 quadratic form. Okay, now let's give some general theorems about positive and negative definiteness and positive and negative semi-definiteness, theorems that generalize the theorems that we obtained in the n equals 2 case, generalize these to any n. So here we have a theorem that generalizes our theorem about positive and negative definiteness, and then after that we'll go on to look at semi-definiteness. So in this theorem, what does it say? It says the conditions, necessary and or sufficient conditions for an n by n symmetric matrix, because we're only worried about symmetric matrices, to be positive definite. So let's focus on that one first. To be positive definite, a sufficient condition is that all of the leading principal minors be positive. Now recall that in our 2 by 2 case, in the n equals 2 case, the conditions were that the upper left diagonal element A11 had to be positive, and the whole determinant had to be positive. Well, those are just the 2 leading principal minors of that matrix A. So indeed, this is generalizing at least that 2 by 2 case. And what does this say in the 3 by 3 case? It says that, well, in fact, let's even write it down over here. In the 3 by 3 case, this says that A11 has to be positive. It says that the determinant A11, A12, A21, A22 has to be positive. And third, that the determinant that's 3 by 3, which is the original determinant, the original A. So let's just write that as determinant of A has to be positive. So this looks just like the n equals 2 case, except that in addition to the upper left entry and the whole determinant, I've got this leading principal minor that also has to be positive. And this is sufficient to guarantee that the quadratic form will be positive definite, just like we had this and this being sufficient without having to consider the remaining diagonal element in the 2 by 2 case. So this is sufficient, as this says here, this is sufficient. All leading principal minors are positive. But then it says necessary is all principal minors have to be positive. And that means that not only does this have to be positive, but A22, positive, and A33 positive. And it also says that, and I'm not going to write all these down, it says that all of the order 2 principal minors have to be positive, and there are 2 more of them. There is the order 2 principal minor containing the first and third rows and columns. I already have here the first and second rows and columns, and of course there's the third leading principal minor, principal minor, not leading principal minor, and that is that the second and third rows and columns have to be positive. So you can see here it says the sufficient condition is that all leading principal minors be positive. The necessary condition is that all principal minors be positive. Now this is a little unusual in math. Usually it is the case, and in a certain sense it's the case here too, but it's a little tricky. Usually it's the case that you have a stronger condition as a sufficient condition, and a weaker condition is necessary condition. You need a strong enough condition to guarantee that, for example, we have positive semi-definiteness, but often the thing that you're interested in, like positive semi-definiteness, doesn't actually guarantee that strong condition, it guarantees a weaker condition. Here it's just the reverse. And so it seems quite unusual that here the necessary condition is the stronger condition, all principal minors positive. But notice the reason that's true here is because of the unusual situation that if the leading principal minors are positive, that's enough to guarantee that all the principal minors are positive. So that's why it comes out this way. And you can go back to the n equals 2 case to see exactly how that works with each of the conditions. In that case, we had that A positive and the determinant A positive was sufficient, and that was enough to guarantee that C was positive as well. So that means that this, in fact, altogether was a necessary condition. And of course, this is sufficient as well. So the same thing is true here. The necessary condition of all principal minors being positive is, of course, sufficient, because even the weaker all leading principal minors being positive is sufficient. So again, a little bit unusual, and that causes a little bit of trouble for people thinking about these, I think. And I have to say that even for me, occasionally that kind of looks a little funny when I come back to it and don't think about it for a while. So that's the case for positive definite. We've written it out for n equals 3. If I wrote it for n equals 4, the sufficient condition would be A11 greater than 0, the 2 by 2 minor greater than 0, the 3 by 3 leading principal minor positive, and the whole 4 by 4 matrix, its minor, the whole 4 by 4 determinant being positive. That would be sufficient. But in fact, if we do have something that's positive definite, all the leading principal minors to be positive, and there's a bunch of them, of course. There's these 4, there's probably, I guess there's 6 2 by 2s, there's 4 3 by 3s, and there's this one. So that's 1, 4, 6, and 4. That's probably 16. Okay, there's 16 leading principal minors, and they're all positive if the quadratic form is positive definite. And of course, in the negative definite case, that's a little trickier, because it says that all of the order K leading principal, all the leading principal minors have to have sign have to have the right sign. Let's put it that way. So recall in the n equals 2 case, that what we had for a negative definite was that a had to be less than 0, c, of course, had to be less than 0 too, and the determinant of a had to be positive. So the sign of the leading principal minor was alternating between negative for the 1-by-1s, positive for the 2-by-2s, and what this generalizing theorem says is that in the 3-by-3 case, it's going to have to be the case. In fact, we can just go up here and see. In the 3-by-3 case, it says that all of the order 1 leading principal minors have to have sign -1. So all of these have to have the sign -1 to the k, where k is 1. So let's just make that a 1 here. That's kind of a little bit of a mess. So let's take this to it, which is just -1. So that means that this has to be negative, this has to be negative, and this has to be negative. That would be necessary, but of course sufficient is just that this is negative. Then this has to be positive because here I have -1 to the k, and k is 2. It's an order 2 principal minor. And so here this determinant has to be positive according to this sufficient condition. And here I have -1 cubed, -1 to the 3rd power, because this is a 3-by-3 order 3 principal submatrix. So this, again, has to be negative. So just like in the n equals 2 case, the leading principal minors, of which there's only these 2 in the n equals 2 case, they have to alternate in sign, and they have to alternate in sign starting with negative for the 1-by-1, negative for A11, which you can see is going to have to be true if I'm going to have a negative definite quadratic form, because I could have all the variables except x1 be 0. And if x1's not 0, x1 squared is positive, A11 is going to have to be negative to make that a negative definite quadratic form. So sufficient condition, A11 less than 0, this 2-by-2 leading principal minor greater than 0, the 3-by-3 leading principal minor, the determinant itself, negative. 4-by-4, A11 is going to have to be still negative because it's still order 1. This is still going to have to be positive. That's going to have to be negative, and the 4-by-4 determinant of the whole 4-by-4 matrix, that's going to have to be positive. So those are the sufficient conditions to guarantee that the quadratic form will be negative definite. And what are the necessary conditions? Well, those are necessary, but in fact, if those hold, then all the leading principal minors will have the right sign. All the leading principal minors of order 1, all the diagonal elements will have to be negative. As again, that one part's obvious for the same reason that we saw that had to be negative. And all of the 2-by-2 principal minors, leading or not, got to be positive, and so on down the line. And so that will work now for any n. And so we have a complete theorem for our positive definite and negative definite cases. And by the way, just let me add as an aside, we could have expressed the positive definite in terms of the sign being something to the k, but then we would say the sign would have to be the sign of 1 to the k, not -1 to the k is positive. But of course, that's always positive, so you just drop that out, and that's subsumed in saying that the principal minors are all positive, because this thing's always positive. So that would have made things look more the same between positive and negative definite, but I think it would be a little obscure for the positive definite case, unnecessarily so. So that's the situation for positive definite. we now have a theorem that gives us both necessary and sufficient conditions for a quadratic form to be positive definite, negative definite, and we've already seen that positive definite is the same as strictly convex. We've already seen that negative definite is the same as strictly concave, and those are going to be showing up very shortly when we talk about optimization, because we're going to need to we're going to get both necessary and sufficient conditions for optimization that involve our second order approximation to the function being maximized or minimized. That second order approximation will involve these quadratic forms. And so that's the first place that we're now going to see positive and negative definite things showing up in economics. Okay, so now let's look at our theorem that tells us when we will have a quadratic form that's positive or negative semi-definite. And to do that, let's take off what we have over here, and then I'm going to write down all 7 of the principal minors for the 3x3 case, and then we'll use those to talk about this theorem about semi-definiteness.